Well, I asked you to do a little astronomy last night.
How do you know where something is in the sky?
I mean, we can't all be Peter Pan, second star on the right, straight on till morning. How do I figure out where something is?
We've been keeping track of where the stars are.
4,500 years. We've been keeping it in writing for at least 3,000 years.
The oldest records we have of phenomena in the heavens
Date back to about 1200 BC.
How do you figure out where something is up there?
Well, that tells me where it went and where it's going, right? But still, how do I, let's say Venus is there. What do I mean by there? Because clearly, what I don't have an X, Y, Z to measure that with, right? I need to make up some ideas of coordinates. And it turns out that the way we do this is based on the fact that the Earth is not
Properly vertical in the heavens.
what I see here are two circles going around the Earth, the equator of the Earth, when I look at it north to south, and then this red circle called the ecliptic. Anybody know what the ecliptic is? I'll give you a hint. This picture is better off that way. The ecliptic is the plane where the sun and all of the other planets lay. The Earth is tilted 22.5 degrees. That's the difference from here to here. This is the middle of the Earth, but the axis of the Earth tilts. And when it's summer, the northern part is tilted towards the sun. And when it's winter, the northern part is tilted away from the sun. So that's why when it's summer up here, it's winter down there. Okay. To measure the position of a star, they don't use X, Y, and Z. They use two angles. And the angle comes from the line we make with the sun on the equinox, beginning of spring, where the prime meridian, we measure around, and then we measure an angle up. We have the right ascension, how far we have to go to the right, and then how far up we have to go. This always bothers me that they call this declination. Because if I see the word decline, my brain says I should be coming down. And that makes more sense to me to be coming down than to be going up. Because we're measuring here from the equator and we're measuring along the equator rather than along the ecliptic. You get it? We look at the Earth as the center of the universe. So we think of it this way. This, by the way, is the prime meridian, one that goes through Greenwich in England. That's why we call it Greenwich Mean Time, because that's where we started. You know why? Because the big observatory was in Greenwich. Okay. I want to take this idea and I want to make it more abstract. I actually want to use declination instead. So I'm going to think of my coordinate system based in a sphere. And if I'm in a sphere, rather than use this one, I'll use an arbitrary sphere. So let's create our three-dimensional coordinates. And we'll have some point out here, P. And its typical coordinates are X and Y and Z. So there's the Cartesian rectangular normal coordinate system for me to look at. Yes? I don't like this. I'm going to change it. But I'm going to think in terms of a sphere. So I start with my arm along the x-axis and I measure an angle. The right ascension would be measured from the axis until I get to the angle under the point. Wait a minute. That would be the angle in the xy plane from the origin to the point under there. So this is the point x, y, 0. I want to use this angle. I know that angle. I've already used that angle. What angle is that? Look at what we did yesterday. Aha, almost. Tangent of theta is equal to that. That's our same theta that we were using in polar coordinates. That's the same angle in the xy plane. I'm going to call it theta. It's the same bloody angle. And now I say to myself, rather than coming up, I'm going to come down. Come down from where to where? Well, I think of the line going from the origin directly to the point. And I'm going to come from the z-axis down to that. So this is a declining angle. You start straight overhead and you come down until you hit this point. I need a new name for this angle. I've already used theta. I'll use a different Greek letter. We'll call this one phi. I haven't quite figured out what this one is, but I need at least one other coordinate. Because right now, I've got a direction and a direction. Go that way. What's the next thing you should ask? How far do I go? Radius. The radius of the sphere that contains that point. Because I've already used r, they use the Greek version rho, so I'll use this little rho here. And then we will have spherical coordinates, rho, theta, phi. How far out? Which direction in the plane, and then which direction down from overhead? Question for you. I have a formula for theta because it's the same theta. What's my formula for rho? Rho doesn't go just in xy though. Because rho is going that way, right? Not that way. The distance square root of x squared plus y squared would be the distance here. I'm going up this time. Now I got to figure out phi. I have a sneaky idea. I'm going to take a triangle here. I'm gonna go from the z-axis straight along above this until I hit the point. That makes this a right angle. I'm going in the same direction as the line in the XY plane. I'm just up here. Let me grab that triangle. This height right here, that's Z. I just slid this triangle out and laid it flat. Where's the angle phi in this triangle? Okay, people, trig time. What trig function of phi can you tell me about? If I have the adjacent, I have the hypotenuse. Like I have a function for theta, I end up with a function for phi. Cosine of phi is adjacent over hypotenuse. Um, hang on a second. This is if I have rho and theta and phi, I can get x and y and z. I'm sorry, if I have x and y and z, right? If I have x and y and z, you work out rho, then you work out phi, and then you work out theta. I can do this. This goes from x, y, z to rho theta phi. So from Cartesian to spherical. We did this particular example yesterday. Only yesterday, we were working in cylindrical. How do I change this to do spherical? When we did this yesterday, we said, oh, x and y are both negative. We're going to be in the third quadrant. We use that to figure out theta. So I get the same theta I did yesterday for this point. But now I'm just saying, okay, so we're going to go that way in the third quadrant, right? First quadrant, second quadrant, third quadrant. And then I got to go up. So I need to know how far out my arm I go and what angle down that is. We can do these in any order, but you have X, Y, Z here. Which really means you can do rho or theta first. But you can't do phi until after you've done rho. By the way, this picture appears here. This picture appears on page 1045. And another version appears on page 1046. square root of 3. Inverse tangent of square root of 3 would be pi over 3, but that's in the first quadrant. So we want 4 pi over 3 to make sure I'm in the third quadrant. And then cosine of phi is z over rho. So I do the inverse cosine. And unfortunately, that's not a nice reference angle. That's something ugly. What'd you get? That's in radians. If you did it in degrees, you get 50.2 degrees. In this case, I know it's easier to work in the same unit both times. So the fact that I did theta in radians means I would prefer to see phi in radians. But if you want to, you could give me theta in degrees and phi in degrees. I wouldn't have a problem with that. You just better use the degree mark if you use degrees. The star charts we use today are written in ascension and declination, as opposed to in this type of spherical coordinate. They measure up from the equator rather than down from the North Pole. Again, not my choice. This is what they decided to work with. But converting from here to here is actually fairly easy. How do I get my phi angle from their declination? How do I get my angle from theirs? There you go. That's it. Now, that's true when my declination is positive. But if I'm looking at something in the southern hemisphere, my declination will be negative. I won't actually be able to see that with my naked eye since we're in the northern hemisphere. So that changes what part of the sky I can see. But based on this idea, if you're in the southern hemisphere, your declination is going the other way. In which case I would have to add 90 degrees because I'm always coming from the North Pole. I'd add and go down. How do I work the other way around? If I know rho and theta and phi, how am I going to get x and y and z? Advantage, that equation can be solved for z. That one's easy. But how do I get x and y? Let me go back to that stupid picture I had a moment ago. Let's slide back up the screen here. I have rho and theta and phi. I need to get x and y. We already figured out z. How do I get X and Y? X and Y, right? That's in the XY plane. That involves the triangle that's flat. But that's the same triangle we were using for polar. So that should be R cosine theta, R sine theta, right? I don't have an R. I have rho. I don't have R. How am I supposed to get R? This is R. Yes? Where's another segment on this piece of paper that's the same length? Wait a minute. That means that right here is the number I need to figure out. What length is that? Remember, this time I know rho and phi. How do I get that length? I'm doing trig again. I'm happy about this. Yeah, because that's going to be the same length as down here. I don't know what x squared and y squared are yet. I don't know x and y. I only know rho, theta, and phi. How can I get this length from that triangle? Rho sine phi. And that means that this radius right here, that's rho sine phi. Oop, not theta, phi. That means here, when I go to do this triangle, I use r cosine theta and r sine theta. So x is rho sine phi cosine theta, r cosine theta. And y is r sine phi sine theta. Sorry, rho sine phi, r sine theta. But I had to figure out the r from the z rho phi triangle. So if I give you x, y, z, you can now find rho theta phi. And if I give you rho theta phi, you can find x, y, z. I'm going to end up with crappy angles this time. 4 comma negative 4 comma, oh, hell, we'll do 4. I'm giving you rho theta phi. My angles suck. We're going to get some really weird looking volumes here, aren't we? Think about this. This says you go out a distance 4 at an angle. Crap, stop. Rewind. Stop. Time out. Hang on a second. Let me explain to you why I messed up. Let me go back to our picture of a sphere, right? Picture your ball.
You go out any distance you want, positive or negative for rho. You can go at any angle you want for theta. What's our typical range for theta? 0 to 2 pi. How about phi? Phi starts out up here. Where does it end? What's the biggest phi I could use? But if I go all the way up, wouldn't it be easier to go down the other side? If I always measure from the North Pole down, then I never want phi to be bigger than straight down. Which means the biggest value I should have for phi is here's it. Theta goes all the way around the circle. Phi only goes halfway. It's going to stop at pi. Let me actually put some reasonable angles in here. Convert 4, 3 pi over 4. 5 pi over 6. Cartesian. Now, before I even start actually working this out, I'm going to start with the angles. X and Y, right? X is negative 3 pi, sorry, positive 3 pi over 4. What quadrant do I end up in? So I'm going that way. Negative, negative second quadrant, negative X positive Y. I measure an angle of 5 pi over 6 from overhead. Which direction do I end up pointing? How many degrees is that? Come on, y'all have calculators, not doing this crap. So I go from here, I go in that second quadrant, I go 150 degrees. I'm going to end up down there somewhere. Wait a minute. 1, 2, 3, 4, 5. I will be in the 6th octant. Second quadrant, but down. And then I go out 4 units. Wait a minute, if I'm in the second quadrant, X is negative, Y is positive, but I'm going down, what's Z? I hope so. Let's find out. This is rho, theta, phi. 4 sine phi times cosine of theta. Y is 4 sine phi sine theta. And Z is 4 cosine phi. Wait a minute, I know these numbers. Sine of 5 pi over 6. 3 cheers for the unit circle. Cosine of 3 pi over 4. Hey, the 4 cancels with the 2 2's on the bottom. I get negative square root 2. 4 sine of 5 pi over 6. Sine of 3 pi over 4. What's the sine of 3 pi over 4? Hey, those cancel.
X is negative, Y is positive. What's Z? Z is 4 times the cosine of 5 pi over 6. Pi over 6. The negative version, so that's negative root 3 over 2. Lo and behold, X is negative, Y is positive, Z is negative, exactly like we thought it was going to be. X is negative, Y is positive, Z is negative. Objects that are spherically symmetric are easier in this coordinate system. If I want a sphere is really easy. What are my boundaries for theta and phi if I'm doing a sphere? Correct. Now, what if I told you, instead of phi going from 0 to pi, I want phi to go from 0 to pi over 4? What shape does that make? Not just the dome, but the inside of it as well, right? So let me think about a stick. A stick would go from 0 to 2, so I'd make a stick of length 2. And then I would allow that stick to go around as far as I want. I will only allow it to come down to 45 degrees. So I would get not just a dome, I'd get the cone underneath it. I would get something, looks like a freaking snow cone. I'm not making it up. There you go. The top of the ball cut out at an angle of 45 degrees gives me a snow cone. This illustration's on page 1048. And I tend to think of it exactly the way I just described it to you. I think of a line going out. I think of the angle coming down. I think of that sweeping out a region. Remember when we were doing volumes of rotation, I brought in those little party toys that look like expanding paper things? That's what I'm describing here. We have this shape, this wedge in this middle picture. We spin it around. Isn't it pretty? Okay. I have a new coordinate system. If I have a new coordinate system, I want to do calculus in that coordinate system. So I need to figure out how to do a triple integral of some function dv in spherical coordinates. Mommy.
The problem with working in spherical coordinates is the same problem we had
working in polar. My little box doesn't look the same anymore. When we did polar, it got bigger as we went out, right? That's why it's r d theta. But now it's going to get bigger this way too as we go out. My little box changes in two different directions. Page 1047. Not only does it change as theta gets bigger, it changes as phi gets bigger. It's a wedge that's got sloped sides, both left and right, as well as top and bottom. And then it's got the curve on the outside and the curve on, shit. My dv isn't a box, dv changed. But I know how x and y and z change, right? I'll take x and I'll write rho sine phi cosine theta. I'll take y and I'll write rho sine phi sine theta. And I'll take z and I'll write rho cosine phi. And when I write them in that order, it helps me remember the first two have the sine of phi, the last one has the cosine of phi. And so it's r cosine theta, r sine theta, like it is in polar. But dv has to change too. For the moment, I'm going to ask you to trust me. I will show you where this comes from on Monday. It's bad enough that I had an r squared, an r d theta. Now I've got a rho squared sine phi. What the? I promise I'll figure out where it comes from. So if I'm going to do an integral, and the integral is, say, bounded by balls, spheres, or cones, like we were just describing, it might actually be really, really, really good to do it in spherical coordinates. An example, I won't do it all the way through, I just want to do the setup. The triple integral over the region E of x squared dv. E is bounded by the xz plane and y equals the square root of 9 minus x squared minus z squared, and y equals square root of 16 minus x squared minus z squared. Now, my first reaction is, what the absolute is that? All right, wait a minute. The xz plane. The xz plane is where y is 0. I want stuff to this side. Well, what are these equations? If I take that equation and I move it over, I get x squared plus y squared plus z squared equals 9. What's that the description of? Of radius centered at. So what's the other one? Exactly, because it'll be 16. Now, again, I think pictorially. I think in pictures here. But I want stuff to the left of the XZ plane. I have a ball of radius 3, but I only want the left part. I have a ball of radius 4, I only want the left part. The piece I want is between those two balls. On the XZ plane, I will have a circle of radius 3. On the XZ plane, I will have a circle of radius 4. And on the left side, sorry, wait a minute, on the right side, these are positive square roots. Positive square roots, right side. On the right side, I'll have hemispheres. So I need you to go down to the cafeteria and steal a soup bowl and a salad bowl or pasta bowl and put one inside the other and set them on a piece of paper. Yeah. You go buy bowl sets at the grocery at Walmart, right? I need a set of mixing bowls. Okay, I've got a 3 mixing bowl and a 4 mixing bowl, one inside the other. Now, how do I describe this region in spherical coordinates? What's the smallest radius I'm allowed to use for this region between these two spheres? And the biggest is 4. Now here's the other two questions are angles. Phi measures from the North Pole down. Theta measures from the positive x-axis around. So clearly I can start at the positive x-axis. What's the smallest value of theta I can use? And if I go around, where do I stop? Exactly. I didn't draw it in, but you could draw the horizontal part of your circle as well, the equator. I'm a crap artist, people, but at least a crappy picture kind of helps me think. Now, pick a direction between 0 and pi. I don't care which one. Might as well use pi over 2. I'm going out the y-axis. From the North Pole, how far down do I get to go? I get to go all the way to the South Pole. All of my boundaries are numbers. You ready for the best part? We were doing this integral, the integral of x squared dv, right? The integral of x squared dv. Now, this time I'm going to wait to write the limits. What's x? X is rho sine phi cosine theta. That gets squared. dv is rho squared sine phi, d rho, d theta, d phi. Hey, now I know what order to put these in. Rho goes on the inside, theta goes next, phi goes on the outside. Now, before you freak out and look at me like, this is nuts. Everything inside there in the integral is multiplied. I get to do my favorite thing. I get to do my favorite thing. What's my favorite thing here? Houdini. How many fees, how many rows do I have? I got 2 here because it's rho squared, and I got 2 more. So I'm going to get the integral from 3 to 4 of rho to the 4th, d rho. How many theta things do I have? Be careful, because that sign is in phi. And then 0 to pi, I got sine squared phi and then another sine phi, so I end up with sine cubed phi. The first integral is power rule. That's easy. The second integral requires me to do the square reducing formula. The third integral is a use substitution, chapter 7, section 2. I know how to do this. Oh, thank God. I will say the same thing I said yesterday. The hardest part is setting up the region. The integrals themselves, we already have the techniques. On Monday, I promise to show you where rho squared sine phi comes from. I promise to show you where the r in r d theta comes from. We're going to generalize this idea to any transformation you want, not just spherical and circular. I will see you all then. Have a wonderful weekend.